Now, since it's not always feasible to get a population data set, we have to sometimes take samples. And that's more often than not, we're going to have to take samples to begin with. And so that leads us to the definition of a sample variance and sample standard deviation. All right, they're going to have very similar definitions to the population one. One of the main key things is that they're represented by Latin letters instead of Greek letters. Because remember, sample statistics have Latin letters, whereas population characteristics have Greek letters. And to define the sample standard deviation, we first have to define the sample variance, which is going to be the sum of squares, again, divided by n minus 1. Right? And since we're dealing with a sample, that minus 1 kind of compensates for the fact that we're dealing with a sample and not a population. And once we have our sample variance s squared, to get the sample standard deviation, we take the square root of that. So it's going to be the square root of the sum of squares divided by n minus 1. And in symbols, the sample standard deviation is the square root of the sample variance. And just like we did in the example at the end of the first page, here's the breakdown for all the steps that we have to take. First, we have to find the sample mean. We take the sum of all the data values divided by the total number. We find the deviation for each entry. Then we square each deviation. We take all those values that we have, we add them up to give us the sum of squares. Once you have the sum of squares, you divide that by n minus 1 to give you the sample variance. And finally, you take the square root of the sample variance to give you the sample standard deviation. And it really helps to lay this all out in a chart, like the last example on the first page, so that you have everything nice and organized. And that leads us to figuring out how much of our information or data is within certain standard deviations once we have that calculation. The first theorem we're going to see is called Chebyshev's theorem, and this applies to any sort of distribution that you're looking at. So it could be really nice, like a symmetric one that looks like a bell curve, or it could be uniform, or it could be left skewed, right skewed, or it could just look like a wave. It could be all over the place, but this theorem applies to any type of distribution. And it begins by saying the portion of any data set lying within k standard deviations, and we take k to be greater than 1, of the mean is at least this quantity, 1 minus 1 over k squared. Let's look at what that means. So for 2 standard deviations, when k is equal to 2, in any data set, at least 1 minus 1 over 2 squared. Right? And if we do the calculation, we get 1 minus 1/4, which gives us 3/4. 3/4, you want to interpret that as 75%. So Chebyshev says that in any data set, at least 75% of the data lies within 2 standard deviations of the mean. And if we look at k equals 3, in any data set, at least 1 minus 1 over 3 squared, which is 1 minus 1/9. And if you get common denominators of 9 over 9 minus 1 over 9, you get 8/9, which is roughly about 88.9% of the data is going to lie within 3 standard deviations of the mean. Let's look at these examples here. So we have just 2 histograms. We're told what the population mean and the population standard deviation is. And so we're able to analyze how much data is within a certain number of standard deviations. This question is asking for 2 standard deviations. Why don't we give some sort of context to these 2 graphs? why don't we talk about age and the number of people of that age? So maybe age on the horizontal and the frequency of said age. All right, so this is 2 towns or 2 cities or 2 states, whatever you want to talk about, and we're just looking at comparing the distribution of ages. So over on this left-hand side, the population mean age is 31.6, and the standard deviation is 19.5. So if we look at mu minus 2 standard deviations, that's really 31.6 minus 2 times 19.5, which gives us negative 7.4. But that doesn't make sense as an age. And so contextually, since we're talking about age, we have to stop at 0. We're not going negative age at all. And for mu plus 2 sigma, we have 31.6 plus 2 times 19.5, which is going to give us 70.6. And so if we apply Chebyshev's to this distribution, it says that about 75% of the people living in this city, so 75% of people are between 0 and 70.6 years old. Because we're looking at 2 standard deviations, we have 2 here. We need to go below the mean and above the mean. And that tells us 75% of all of our people are between 0 and 70.6 years old. Over here, we have a different mean and different standard deviation. So we have to do the calculation over again. So mu minus 2 sigma is 39.2 minus 2 times 24.8, which is again going to give us a negative number. Since we're talking about age can't be negative, we just stop at 0. And we have to do mu plus 2 sigma, which is going to give us 88.8. So for this city or town or state, we would be able to conclude by Chebyshev's that 75% of people are between 0 and 88.8 years old. All right, so let's compare and contrast. Over here, we have a younger average and a smaller standard deviation, which means that if you calculated the average age of everybody here, it's younger and there's less spread on the amount of people with higher ages, let's say. Whereas over here, the average is higher and the standard deviation is larger as well. So there's a lot more people that are either older or younger than 39.2, whereas over here, there's more people that are closer to this 31.6 age than there are people closer to this 39.2 age.